So this is the video abstract for section 4.1 on areas and distances. In this section, it really feels like we're doing something very different from what we've been doing. This is a lot like section 1.4, where we're introducing a problem, exploring it, and then eventually that led into all the other discussions of limits and all of that, and derivatives. And so we're going to see that same thing happening here. So here's the kind of problem that we're looking at, that we're interested in. We're interested in the area under the curve y equals x squared plus 1 from x equals negative 1 to x equals 3. Now, why one would be interested in this area itself is kind of silly, but this does have applications if, say, this curve were a rate. What we'll find out, this area corresponds to how much whatever that rate is of has accumulated, for example. If this is a velocity at time x, the area is going to correspond to the distance traveled, or actually displacement. This is going to the position. And so these have meanings outside of just areas, but area gives us a nice geometric interpretation of what we're about to do. So that's why I like starting there. So we're interested in this curve, this area here, and if this were 5th grade, what we would do is just split this up into a grid, count the number of little boxes. Actually, we would make it a 1-by-1 grid. Count the number of boxes, estimate, cut it up into smaller boxes. And we're going to do that, but with a little bit more sophistication, because this is really a nice kind of a curve. We have a pretty good idea that x squared plus 1. So what I'm going to do is I'm going to call f of x, x squared plus 1. And as a starting point, we're going to cut this up vertically. This is what's called a Riemann sum, named after Bernard Riemann. There are other ways of cutting up this region. There's what's called the Lebesgue sum. That's something that you don't see until an analysis class, if then. But this is really the simplest way of doing it. This is the classic way of doing it. It's called a Riemann sum. And what we're going to do is we're going to cut vertically. And so we're going to cut at, let's say we'll just cut at 2 for the moment. And we're going to use that, we're going to draw 2 boxes, cut this region into 2 boxes. And we're to be interested in that area in these 2 red boxes, the area from negative 1 to 2 and from 2 to 3. Oh, that's not 2, that's 1. So negative 1 to 1 and from 1 to 3. Notice they're the same width. That's not necessary, but we're typically going to be doing that. And so what's the area of each of these boxes? So the box on the left, that width is 2, and the heights are given to us by the function. The height there, that is f of 3, which is 10, because of the x squared plus 1. F of 1 is going to be 1 squared plus 1, so that's 2. So we're looking at a 2 by 2 area plus a 2 by 10 area. So that's 4 plus 20. An estimate of about 24 for that area. That's not a very good estimate, because we got all this overage here. That's definitely too big. Definitely too big. So that's area with 2 boxes or 2 strips or 2 subintervals. Sometimes we look at it as that's one subinterval and that's the other subinterval, and we're just sort of shining a light up and seeing where we hit. Let's do a little bit better. Let's do it with 4 boxes. So we cut each of these in half, and that's no longer what we're interested in. We'll cut at 2. So now all of our boxes have height 1. We're no longer, there's a lot of this area that we're not interested in. We'll be cutting that 24 figure down a bit. So if we have 4 subintervals, our reference points are going to be here at 0, 0, 1, 2, and 3. The heights at those reference points are what happens when we do f of 0, f of 1, f of 2, and f of 3. So that's f of 0 is 0 squared plus 1, so 1. F of 1 is 2, f of 2 is 5, and f of 3 is 10. So those are our heights for each of these boxes. This is not drawn to scale. Our width comes purely out of the 4 subintervals, and the width of here, they're each width 1. That sometimes use a delta x for that width. width is 1. And so our areas of each box are 1 times 1, 2 times 1, 5 times 1, and 10 times 1. Those ones being there. So that being the width. 1 plus 2 plus 5 plus 10. And so now we're getting an estimate of 17, which is less than our area of 24 before, and probably a more accurate depiction. It's still too big. We can do it again. We could do it with 8. Now we cut it up into 8 subintervals, so each of these boxes gets cut in half. So 8 subintervals. Our reference points are now, cut this up, and that's -1/2, 0, 1/2, 1, 3 halves, 2, 5 halves, and 3. 1.5, 2.5. Our width, I'm doing this a bit out of order, but that's not a big deal. Our width of each of these is 1/2. Our heights are, plug in each of these, f of -1/2, f of 0, f of 1/2, all the way up to f of 3. I'm going to start using a ... because these get tedious very quickly. And from there, we got to do our areas. So our area is going to be that f of -1/2 times 1/2 plus f of 0 times 1/2 plus f of 1/2 times 1/2, all the way up to f of 3 times 1/2. And I've gone ahead and pre-computed these. This product is going to work out to be 5/8 plus 1/2 plus 5/8 plus, and there's a whole bunch of ones in between, all the way up to 5 there. You add them all up, and you get 31 halves, which is, well, not about equal to 15.5. So there's another estimate, a better estimate, using 8 intervals. And we can continue this process. So if we did this with, so let's make a chart here, because that helps us organize. We usually use the number n for the number of subintervals. And what we'll track here is our width, delta x, and then the area estimate that goes with that. So we've seen for n equals 2, our width was 2, and our area estimate was terrible, 24. For n equals 4, we had a width of 1, and our area estimate was 17. For n equals 8, our widths were 1/2. Our area estimate was 15.5. And we can continue this. The more subintervals, the more things we have to add, but the better the precision is. That's the trade-off. And we'll get to a point where it's not tedious to do infinitely many subintervals. If we did this with 16 subintervals, our widths would be that the whole thing was width 4, as we went from -1 to 3. Cut up into 16 equal pieces, we're talking a width of 1/4. And that works out to be, once you do all that grind work, 14.375. We could do n equals 50. Then those would be width of 4/50ths, which is 0.08 compared to the 0.25 there. That estimate would be 13.6576. We could do this with 1,000. Now, I don't want to do that by hand, certainly, but that's 4 over 1,000, which is equal to 0.004. That would get me 13.3493. It seems like they're settling down now around 13. It seems like it's a little bit more than 13. Maybe it's going to keep going down below 13. It's hard to tell at this point, but say we went to 100,000. We're looking at intervals of 1, 2, 3, 4, of super tiny, and we're looking at 13.3335. So now the 13.3 has really settled in. And even if we went up to 1,000,000, we'd be looking at 13.3333. I think there'd eventually be a 5 in there. But that really seems like if we had infinitely many subintervals, it seems like we'd be getting 13.333 repeating. The problem with that, though, is our widths would be 4 over infinity, and that's 0. And also we'd have to add up infinitely many things. We'd have to add up infinitely many things, each of which have area pretty much 0. And that ends up being 13 1/3. That's what limits can do for us. We're going to bring in limits to really, rather than doing infinitely many, we're going to do the limit as n goes to infinity. Because the idea is more subintervals makes more things that get added, but the things that get added get smaller. And hopefully there's a balance that happens between those two. Right. So the area of the region lying under the graph of f of x from x equals a to x equals b is defined to be. This is we have this notion of area coming into this, but they actually define area to be whatever happens when you take the limit as n goes to infinity with n subintervals, with n pieces, which will work out to be, well, it's going to be all these different heights at reference points, height times width, height times width, height times width, the width being b minus a over n, because this doesn't have any n's in it except there. And so that tells us that there's going to be infinitely many, but that tells us that that width goes to 0. This is something that's discussed in Appendix E of our book. This is called sigma notation. The advantage of this is that it is shorter. It's compact. You take this long sum and you encode it this way. This is essentially a for loop if you've done any computer programming. This is for I from 1 to n, and then you add up the s is for the sigma, the sum, f times x sub I times delta I. You need to have some way of finding these xi's, but that's details. But that is the core idea of 4.1, that we can find areas by adding up infinitely many intervals. Now what we're going to be doing with this in 4.2, we're going to introduce a new notation for it. That looks like that. The i's and n's, really since n's going up to infinity, there shouldn't be any i's or n's at the end anyway. And so we have the a and the b marking the interval we're interested in. And we'll find ways as we progress through chapter 4 of actually computing this without having to do this long way. Because this really is a chore to do the long way. All right. Well, thank you very much. I'll see you later.